Hey guys, in this video I want to go over two very specific centripetal force problems, which are going to be the flat curve and the banked curve. The flat curve is when you're turning, you're turning on a curve that has no angle, so it's just flat, so you're going to need friction to do that. On the other one, you're going to be turning this way as if you're sort of on the highway ramp or something, or NASCAR is a good example of this, where there is an angle but there's no friction. So I have either friction but no angle, or angle but no friction, one or the other. All right, let's get started and see how this looks. Okay, so the first one we're gonna start with here is a flat curve. It says find the maximum speed. So I want Vmax. That's a 800 kilogram car, can have while going around a flat curve of radius 50. So the radius is 50 meters of the curve. Okay. You are at the edge of the curve as you're turning, so your little r is 50. Without slipping. If you're not slipping, that means that you have static friction, okay? That means you have static friction. If the coefficient of friction between the car and the road is 0.5, so I know that mu static is 0.5, okay? How do I do this? Well, I'm looking for a velocity in a circular problem. I'm going to use F equals ma. Another hint that you would use F equals ma is that friction is a force, and there's a reference to friction here. Okay, I want to quickly sketch what the forces look like here. It's not like an official free body diagram, just a sketch. Mg is pulling this thing down. Imagine this is the x plane, and normal is pulling this thing up. Now, if you're going around a circle, here's a top view of the car. Every time you're going around a circle, your velocity is tangential, but you have a centripetal acceleration. The only way to have a centripetal acceleration is to have a centripetal force, because F equals ma, right? You need an F to get an A, so you need a centripetal force to get a centripetal acceleration. So there has to be a force pulling you to the center. And for the flat curve, you need to know that that force is your static friction. One way to think about this is just try turning without friction, right? On an icy road, or if there's oil in the road or something, or if you're going too fast or whatever. So if there's not enough friction to make you turn, you don't turn and you go straight through. So you need to know that friction is what keeps you turning. Now, even though the car is moving, the wheels are moving, this is static friction because it's not slipping. Remember, static friction is when you're moving without, when you're not moving or moving without rubbing. Kinetic friction is when you're rubbing on two surfaces. Here, the wheel isn't doing that. So it's going to be static friction, okay? So the only force in the centripetal direction is static friction. It's towards the center, so it's positive. So here's an example of where friction is positive. So positive friction static equals MAC. Now I'm looking for velocity, and hopefully you know there's a V in here. AC is V squared over R. There's a V hiding in there. So I can just replace AC with V squared over R, okay? We're basically 80% done in terms of things you need to know. And I just want to tell you that the rest of this is really just making this look pretty, right? So I have to get the V to look in, to be written in as simple terms as possible. Meaning, I'm going to rewrite everything I can into simpler terms. So for example, friction can be written as mu static normal. And normal can be rewritten as well. So you're almost always in these kinds of derivation problems, you want to rewrite friction, you want to rewrite normal until they're in the simplest form. I hope you see here that normal has to equal just exactly mg, because those are the only two forces in the y-axis. So I can rewrite this again as mg, and this is mv squared over r. So notice that the masses cancel, okay? And now I'm ready to go. There's nothing else I can replace mu with, or g with, or r with. So if you move stuff around, it's going to look like this. V squared equals gr mu s. Now I'm writing this in a very specific way. You might be wondering, why did you write in that sequence? You moved the letters around, or why did you leave a square there? There's a reason for this, which I'll show you later. So I want you to remember the equation this way. And by the way, you should remember this equation for a test, because if it shows up as a multiple choice question, if your professor does that, and you remember this equation, and you know it's a flat curve, you can kill this right away. Okay, so that's how this works. Let's now actually calculate the number. This is the least important part, but let's do that real quick. It's the square root of g, which is 9.8, r, which is 50, and mu, which is 0.5. And if you plug all of this in, you get a 15.4. Okay. At the most basic level, this is how you can figure out how quickly you can go around a turn. So if you work for the city and you're trying to figure out what kind of speed limit to put on this turn, you'd probably put like 12 or 10 or something, right? Because you know people are always going to drive a little faster or try to be a little drive a little faster. So that's how they post speed limits. They just decrease that by some percentage or whatever, and that's that. Okay. So if you're going 40 on a 30. You're not that special. They knew you were going to do that. They lowered it because they knew people are always going to try to do stuff like that. Anyway, so that's easy. That's the flat curve. Now the banked curve is far more complicated. Let's jump into that now.